here we're going to continue on what we started off earlier. We looked at, before this, look at what's the electric current, how to define it. And then we looked at what's a coulomb, we looked at the marble challenge and all things like that. Now the last part of the theory for this chapter, oh my goodness, we're done with the chapter. Well, that's a theory part of it. There's applications, all applications. The last theory we want to look at is how to think about current in a conductor. Okay, now specifically in the conductor, what does it mean? How to derive an equation for it? This one you must know. Later I will come to it. But you must know how to derive an equation and for all kinds of conductors. First things first, what is a conductor though? You don't have to memorize this for A levels, but it's just for you to know electrical conductor usually is things where you can conduct electricity. What does that mean? Things where if you connect a circuit, electricity will flow through it. That's a simple term. For example, if I take some random plastic comb and then I connect it to a socket, it's not going to conduct electricity, no. Maybe if I took this metal carabiner, it might conduct electricity, I might get an electric shock. Okay. Wood, maybe not. If I put a wood in the socket, connect a circuit, doesn't work. So some elements can be, some materials can be conductors, some cannot. The key point, how you know whether they can conduct or not, is whether their charge carriers can move between their atoms or not. Here's a very quick background for those of us who are not sure, like, atoms, what's all this thing? Forgot already, missed this one as chemistry last time. Well, let's take a look. So here, let's say I have a copper wire. Copper is most commonly used in electrical wiring, your house, your phone, everything, copper, for a multitude of reasons. But anyway, let's say I have a copper wire. I zoom in a bit on that copper wire, and if you really can zoom in, you see there's a bunch of what we call atoms, all packed very tight together, all clumped together. So each of these, what is it called? I was going to say each of these BG, each of these ball atom is a copper atom. Okay, so I say copper. Cu is a short form of writing copper atom. So if I zoom into one particular atom, zoom some more, ta-da! Oh, what is this? Don't panic. This is called the structure of the atom. First, you got the middle part, which is 29 protons. So a lot of positive. And then to balance that out, there should be 29 negatives, which is the electrons around the middle. So negative. These are what we call electrons. You see how they're arranged in circles, right? Each circle, the layer is what we call a shell, electron shell. Okay, so let me almost there. So look, wow, very crowded, very happy, like an extended family. Except there is one fella out here, which is alone. So lonely. It is so lonely. Okay, so you have one lonely atom outside. They often call it the valence electron. This atom, very sad. Sometimes it will get lost. Sometimes people will snatch it away. Sometimes it get donated to some other family. So this poor lonely atom on the outer shell often get lost from the family of the atom. So it's also kind of good because they are very free-spirited. These are also what we call free electrons. Free, because they can easily just come out and then go somewhere else. They are not bound very tightly. Or if you are curious to know where, ask a friend who takes chemistry there. Hopefully they can explain to you. So anyway, this outer electron can come out, and that's what we call charge carriers that can move between atoms when voltage is applied. Okay, so let's say I apply voltage. I make this part of the wire, I put positive, very high potential. Then I put a negative on the other side, lower potential. Wow! Suddenly, all this lonely electron outside will feel a force. Got electric force pushing me. So very easy, they can come out of the atom, so they'll come out. Boing. Then the electron will start to travel. In which direction? Towards the positive. That's because of electric force. We have seen that before. That's in chapter 17. Okay, electric fields. If you have a high potential, low potential, there's electric field. and electrons will travel towards a positive side or higher potential because of an electric force. That's all of chapter 17. So that's the whole idea. If you have conductors where electrons can move around, then we call it a material conductor, no? Electrical conductor. Some materials are better than the other, but that's out of the scope for our physics here. That's like physical chemistry, aka material physics. So no. Just so you know, there are lonely electrons in the outer shell that can be free and just move around the whole thing. So you see this lattice, they'll just move around, move anywhere they want to go. But they'll generally follow the electric field. Okay, so that's the introductory idea. Hopefully you can see the electric field behind me here. So that's the introductory idea of what it means to what is a conductor? Why is there even electricity happening? Because the electrons that can escape. Okay, good, we got that. Now let's take a look at how we can think of this in terms of physics to calculate things, calculate current based on all these lonely valence electrons that can come out and be free. So what I'm going to go through here is the derivation of a drift velocity. You know, just now I said the electron can fly all over, right, inside the lattice of atoms inside the copper wire. Well, yeah, that's what we call drift velocity in a way, but there is a formula for it. We need to know how to derive it, and that's only for current. I call it current in conductors. That's related to that lah, conductor. Okay, where were we? Yes, we were saying. Okay, so we have a piece of wire. Ignore the I on the left side first, okay? Ignore that one. Let's say we apply a potential difference to both ends of this wire. Like how when we connect a battery to a circuit, we're applying a potential difference, okay? So, let's say I put the left side as positive lah. And then the right side I put negative, connect to the negative. That means this side is a high potential. Oh, there's going to be so many V's in this section. I'm going to clarify a bit. Potential, I'm just going to use a V like this. Simple and straight. Later you'll see there's volume and velocity of so many V's. Then on the right side, there's low potential. Okay. And inside this conductor, you got a bunch of free electrons everywhere. Let's see, can I just draw tiny little things? There's actually many more lah, but I just draw a few only lah, because not enough space. So once you have applied this potential, there's going to be an electric field in the conductor itself. Where will that field point? Well, high to low, positive to negative. So like what we looked at in previous chapter, electric field E will be pointing in a certain direction. Yep, we know that. And then where will these electrons move though? Well, they will experience an electric force to the left. Okay, so for example here lah, electric force to the left. But they won't exactly travel in a straight line lah. Some of them will go up a bit, down a bit, up a bit, down a bit. But all these things are like velocities. So velocity, and we put a longer tail on the V. So these are what we call velocities. Not R, V, please. So they all experience electric force and they all start moving to that side. To the left there. Sorry, camera is flipped. I'm like left, right. Where is left, where is right? Okay, so all these little fellas will start moving, and that's what we call drift velocity. Electrons are moving, okay. So, one more thing to note. We can use this velocity thing to calculate current, how fast they're moving, how many of them are moving, things like that. But one more important thing you need to know is the area and length of the wire. So area here can mean cross-section area. Sometimes it's a square, sometimes a circle. But here, if it's circle, then it's pi r square or pi d square over 4. Okay, and there will be a certain number of electrons flowing past this area. Very much like what we did with the tube area, right? The tube in the previous video. How many marbles are rolling past this point? Same thing here. All these electrons are going to start moving, and they will pass by the area at a certain rate. So let me write here. Some number of electrons will flow past in some certain time t, or I should say time interval t. It's a note. Okay, And what is their total charge? We also see that earlier. Because of all these electrons flowing past a certain point, it could be here, it could be on this end, okay? Because of all these charge flowing by, there's a total charge Q, which depends on how many electrons are there times each individual charge, E, and E, okay? So this is the total charge. Okay, these are the facts of what's happening in the wire. Now, how do we find this current based on all this stuff? There's a few things to know. We need to put together. The first thing is about this drift velocity. So let me write this down. So drift, why they call drift? Because they're just like floating there to the left. But drift velocity of all these free charge carriers, in this case electrons, we can measure it as, well, what can we say? Velocity, okay lah, we use V. I curve the tip a bit so it's different from the potential V up there. So drift velocity V depends on, think back on kinematics. How do you find the velocity of an object? You take a certain distance. How long does it take to go that distance? Velocity is distance over time. So in this case, let's say you have an electron on the right side, travel a distance L and go to the other side. So okay lah. So that's kind of like a certain distance L, a certain distance T. This D here means change in L, change in T. It's just a different way of writing it lah. Change in L, change in T, I write everything out. Or you can just define it L as change in distance, change in time. Same thing. I'll just write everything out. Okay, so that's one fact. Drift velocity. Okay, we already got an equation. Good. Not yet. We want it to be related to current, although we already have equation for drift velocity. Okay. So what other things can we think about? The other question is, you look on the right side, right? Current is related to charge, but you need to know how many electrons are there, Ne. So, think about this previous picture that we looked at just now. In the copper wire, there is a certain number of atoms. Each atom will contribute one free electron. Okay, so that's a clue. We could define a way to kind of calculate how many electrons are there. Sure, let's throw that in. All right. So we need, this is what people created, and we call this the number density. Okay, this is, well, kind of squiggly line N. That's what we use. And N is what we say the number of free charge carriers, or electrons in this case, divided by a unit volume. This is the way people come up to decide how many electrons are there lah. Say, maybe for copper, there are 500 million thousand electrons in this 1 meter cube. Maybe for aluminium, there is 50 times 10 to the power of 29 electrons, free electrons in this volume. Okay, sure. Whatever that is. People just like to create things to make it easier to calculate, so we don't have to deal with all the chemistry, molar, volume, all those things. No. How 1 mole, 2 mole? Okay, no need. All we need to know is number of free electrons per volume. So volume is meters cube. Okay, volume, I'm going to use this V, which has fancy straight lines. Okay, this is number of electrons, by the way, so I should put Ne. Okay, so we have a few things now. We have, firstly, the drift velocity. We have number density. There's one more thing we need to do to put all these ideas together to come up with the current. This is where the fun part happens. Also, you need to know how to derive these. Previously, we know from definition, okay, what is the definition of current? You remember? We just looked at it yesterday. Not yesterday, the other video. Okay, current is the rate of flow of charge per unit time. So far, so good. Okay, so how do we find what's the total charge that will flow through this this short distance of wire in a certain amount of time. Hint, hint, it's up there. Take a look. Okay, so how do we know? Well, we know that in a short amount of time, you will have n number of electrons. Each of them have an elementary charge E. And that's the total charge, no? Okay. First step. Can we expand more stuff? We want to include the drift velocity stuff here. How can we include that? Well, let's include more stuff. We want this equation to be applicable for all kinds of metals, all kinds of conductors. So we're going to use this number density here. Ne, well, I should erase this E. Oh no, it's gone. This thing can be rearranged to be N equals to number density times volume. So this is rearranged, that's what it means. So I can plug that into N over here. So that will be N, number density, volume of this wire, or this segment of wire, times the charge of each electron. Okay, I think we're good. This equation is evolving. We still have not gotten drift velocity inside this current. That's the goal. We want to get drift velocity inside here. Okay. So how? Volume. Oh, I have an idea. What if we think of volume of a cylinder? Volume of a cylinder equals to the cross-section area. Oh, I should put this V here. Times the length, right? I know that is pi r square h, but this is a shortcut for it. So the volume is actually A times L. So that is another clue inside here. Okay, next step. I shall go to the next line. So let's break down the volume. Volume is A, the cross-section area, times L, times each charge. We're almost there, hang in there. Now this looks very familiar. Can you see how we can involve drift velocity inside this equation? Is there a way we can sub anything? Do you see it? I see it. There's an L over T here, which equals to the drift velocity. There's also a L over T here. Aha. So we can rearrange this NA L over T times E, and that gives us, woohoo! Let's do it on the next line. Current is, drum roll, the final thing. Number density, how many electrons are there per unit volume. The cross-section area of the wire, L over T is drift velocity. Oh yeah, so now it's in the equation. Drift velocity, I curved the V a bit, times E. Well, if you don't want to put E, you can put Q also. Some textbooks will put Q, don't panic, it's the same thing. Here I already say, oh, charge carrier electron, so I put E. So I equals to nave. This is the way you can calculate the current in a conductor. If you know what material is made of, this is called number density. If you know what's the diameter of the wire, you can find area, cross-section area. You have drift velocity, and then of course E is, you know lah. This one is drift velocity. Okay, I actually expanded this out to many steps, but you can actually shorten this to a few steps if you know how to derive this. But yes, you need to know how to derive this. They will say, we will look through a question later, they'll say, show how you get I equals to NAVE. Then you have to think, where do you start? You start from the basics. You start from this thing. And you go through subbing stuff and you get to the end. But yeah, that is the main idea of drift velocity and how that relates to current. Again, drift velocity is, what again? All this average lah. All the electrons kind of drifting to the left. That's what we call the drift velocity here that we are looking at. Alright, so I'll give you time to digest that a little bit. Now before we go to some application questions, example questions. I need to warn you about this. Scientists in the past messed up this current part. Before, was it Rutherford or some other guy who discovered the structure of the atom? They kind of confuse positive, negative charges a little bit. Okay, so here we know obviously like, okay lah, electron moving around, that's the charge carrier. But people in the past did not know that. They thought that it was positive charges moving to the right. They're not wrong. I mean, it fits with the model of electric field. Okay, positive charge move to the right. But in reality, the positive charge is not exactly moving to the right. It's the electrons that's moving around. But there is one problem. They have, by then, because of this idea, this wrong idea, that positive charges are the charge carriers that are moving to the right, they already defined current as moving in that direction. So electrons is moving to the left, but conventional currents, I need to warn you about this. Conventional means like normal law in the books, you will see a I with the arrow. I means current, by the way. Conventional current is the flowing of positive charges. I know some of you who really know your chemistry, you'll be like, doesn't really make sense. Anyway, but just so you know, expectation versus reality, okay, you're familiar with that? Expectation is positive charges moving. And that's what people falsely believe that was wrong, and we're kind of stuck with that convention. But in reality, it's the negative electrons that are moving around in this copper material. Let me show you, okay, just to illustrate in the circuit, I'll show you a simulation. This one is a FET, Colorado FET again, a simulation. You can build circuits, pretty fun stuff. So let's say I connect. See, nothing's moving now, right? Once I connect the wire, the electrons will start to move because there's a battery up here. So let's connect it. Ayo! Fire! Oh my goodness. You know what happened? I did something wrong. We consider wires have no resistance. So what I did is I basically short circuit the battery. So the current is very, 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 very high. And, well, the battery will burn. So let me modify that a bit. How about I put a resistor here? Resistor will slow down the current a bit because it's got resistance. I put another wire here. Aha, look at that. Now it's moving slow and steady. I can change the resistance to make it move slower, faster a bit. Okay, can. Okay. So notice how the battery here is the positive side. Here is the negative side. And yeah, the electrons are flowing from the negative side to the positive side. But if I switch to conventional current, this is what people thought last time was the positive charges moving. So the current I that we use is positive charges moving, and it is the opposite direction. Okay, so here you're moving from the positive to negative, clockwise. Electrons, reality is anti-clockwise. They're different direction. This is just, some people messed up in the past and it was too much hassle to correct all the textbooks, so we just like, yeah, let's roll with it lah. It's just a convention anyway. So just to recap really quickly, one more time, conventional current I, we say flows from the positive, go down, go back to the negative. This is conventional current, which is the I symbol that we use. Electrons in reality move the other way. So electrons are actually moving this way. Electrons moving this way. Okay, just a fact to remember lah. Conventional current is the I that we always see in circuits and things. From today onwards, if you see I in the circuit, that means conventional current. If they specifically talk about drift velocity and electrons, they gotta be careful a little bit which direction they're flowing. Okay, so let's look at some practice questions now.